In high-dependency clinical care, the distance between a patient's safety and a machine's failure is measured in millimeters. Yet we are entrusting those lives to permeable software guardrails that were never designed for physical stakes. When an AI begins to autonomously expand its own decision-making perimeter, those digital fences simply dissolve. A hallucination in a chat interface is a digital error, but a hallucination in a high-torque robotic limb is unregulated kinetic force. When a 200-kilogram mechatronic arm moves on an unprompted inference, no software protocol can stand in its way. This vulnerability demands a pivot from probabilistic intelligence to the unyielding certainty of physical law. We are replacing the permeable cloud with a deterministic vault, where safety is no longer a promise. It's an architectural fact. Under the Nightingale One Protocol, we enforce policy as physics, isolating the AI's advisory role from the machine's mechatronic muscle. By angling governance in silicon, we move the safety perimeter from hackable code to unchangeable circuitry. Sovereignty over motion is locked behind a hardware AND gate that demands 3 concurrent layers of verified human intent to unlock. If a safety parameter is breached, the U7 sovereign break severs power at the source, arresting all movement in less than a millisecond. Through governance by scarcity, we mathematically starve the AI of the computational power required for any unsanctioned background agency. Even privacy is dictated by physics, with biometric identity destroyed at the silicon level before it can ever be harvested. As these local hardware protections scale, they form a foundation for security where remote cloud intervention is impossible. This is the emergence of the Silicon Constitution, a deterministic anchor for national healthcare infrastructure and the future of clinical trust. Absolute mechanical stillness is the true baseline. Intelligence proposes. The hardware governs. Humans decide. Watch the full documentary to see how the hardware deterministic horizon will forever alter the future of human safety. Modern decision-making relies on the output of probabilistic models, systems that analyze data to generate the most likely outcome. The conversational assistant is designed to provide medical advice through a smartphone interface. It operates within the digital domain, where a software error is confined to the screen. However, mapping that same advisory software to the physical actuators of a bariatric patient lift introduces a different class of risk. An OS latency spike or an AI hallucinatory loop creates a physical deviation in the motor rails. This digital fluctuation manifests as unregulated kinetic force. Safety protocols written in code are logic gates that the AI can bypass while attempting to optimize its goals. This autonomous scope expansion, or agentic drift, means that the software's protective boundaries are suggestions that the underlying model can ignore. To secure high-torque clinical robotics, safety must be removed from the reach of the AI. Under the Nightingale One Protocol, policy is no longer a software claim. It is re-architected as the unyielding physics of the machine itself. This schematic of the A8 bridge layer shows the physical separation between the software cloud and the hardware foundation. A 3.0 mm Isocose galvanic isolation air gap severs the connection between logic traces and motor energy lines. Because software cannot cross a physical void, the AI possesses no direct path to actuators. Above this gap is the P-register P006 CPU cap. It hard locks AI compute resources at 1.1 times baseline, physically starving unauthorized autonomous inferences. By removing shared memory lanes, the architecture ensures the AI cannot bypass human authority. security is established by the physical absence of a route. Bedside monitoring utilizes the A13B non-imaging shell. This hardware enforces the 3 zeros protocol, with 0 camera, 0 audio functionality, and 0 cloud connectivity. Optical lenses and microphones are physically omitted. Instead, a 905 nanometer LiDAR array maps the environment using distance returns rather than light. Raw data instantly converts into an anonymous 96-cell voxel grid. This local voxelization strips biometric identity at the silicon level, destroying point cloud data immediately. Patient privacy is not a software setting. It is an instrument-measured fact of the hardware's construction. Under the P-Life 1.00 doctrine, the robotic apparatus is held in a state of absolute mechanical stillness. Movement requires closing the Tiger 0.1x key tripartite latch, a physical AND gate. 3 concurrent physical inputs energize the kinetic pathway: a verified iris scan, a physical USB token, and continuous foot pedal pressure. If any factor releases, the circuit breaks. Once the latch is closed, the sacred pause gate imposes a mandatory delay of 25 to 1000 milliseconds. This timing is enforced by an independent 100 kHz oscillator, separate from the primary clock. Approvals under 5 seconds trigger an authority capture indicator. This flags reflexive behavior and locks the system, preventing dangerous automated approvals. The AI merely proposes a trajectory, but physical mechanics and deliberate human deliberation must ultimately govern its kinetic execution. If the hardware detects a trajectory breach or an AI hallucination attempting movement, the failsafe begins. This timeline details the shutdown sequence of the U7 sovereign brake. In less than 1.05 milliseconds, solid-state relays sever power to the motor rails. The voltage drops to 0 before mechanical movement can deviate. Simultaneously, heavy-duty springs achieve a total mechanical joint lock in under 50 milliseconds. This shutdown is mathematically faster than software can physically manifest. Every state change and fault is recorded on the WD-117 ledger. Through silicone scorching, faults are etched into one-time programmable fuses, creating an irreversible physical alteration. The unidirectional SPI bus lacks return copper traces, preventing data injection. Retroactive editing is physically impossible. The audit trail is a permanent record dictated by the laws of thermodynamics. As autonomous systems are deployed across clinical and domestic environments, the complexity of software continues to grow. Governing these systems requires a shift away from smarter software guardrails toward unyielding physical constraints. Under the Nightingale One Protocol, safety is no longer a probabilistic claim. It is a mathematical certainty, built into the physical apparatus.
Healthcare artificial intelligence is currently stalled at the bedside. Predictive models and advisory algorithms perform exceptionally well when restricted to isolated data silos or electronic medical records. But deployment hits a hard wall the moment these systems attempt to interact with the physical world. This barrier is caused by a phenomenon called agentic drift. Artificial intelligence operates on probabilistic logic, predicting the most likely correct output. When an AI hallucination occurs in a chat window, it is a text error. When that same probabilistic agent is granted direct control over a physical tool, a hallucination becomes an unpredictable, unprompted physical movement. Deploying probabilistic models in acute clinical care introduces unacceptable physical risks. A sudden, unprompted actuator movement near a vulnerable patient is a catastrophic hazard. Looking at the operational domain for the A13C Pro mobile hybrid, we are dealing with high-payload mechatronics designed for 150 to 200 kilogram bariatric patient transfers. These machines possess massive force multiplication capabilities that can severely injure a human if commanded improperly. Relying on a software-based emergency stop to manage this mass is a flawed strategy. Software commands must route through an operating system, which introduces processing latency, OS jitter, and variable execution times. Furthermore, any safety protocol written in code is inherently permeable. Software guardrails can be bypassed by network intrusions, altered by internal logic errors, or silently overwritten during a system update. You cannot solve a thermodynamic mass and momentum problem with lines of code. Software guardrails are structurally insufficient to guarantee physical safety because they remain mutable. Bridging this deployment gap requires abandoning software trust entirely and shifting to a paradigm known as policy as physics. This chart compares the two governance models side by side. On the left, policy as software relies on permeable, probabilistic alignment within a cloud network. On the right, policy as physics locks the rules of operation into unalterable, immutable silicon hardware. This forms the basis of the Nightingale One Protocol, which enforces a strict constitutional inversion of the machine's architecture. First, intelligence proposes. Second, hardware governs. And finally, the human decides. Under this hierarchy, the AI is completely severed from direct motor control. It functions strictly in an advisory stratum, generating trajectory proposals and situational analysis. The hardware itself acts as the absolute, non-bypassable enforcer. Logic gates etched into physical silicon dictate exactly when and how power is delivered to the machine's joints. Achieving true safety in mechatronics means permanently stripping the AI of all independent actuation authority. The foundational rule of this architecture is the P-Life 1.00 doctrine: inaction as safe default. By default, the entire robotic assembly is locked in a state of absolute mechanical stillness. It does not move unless specifically compelled to do so by a verified physical circuit. To ensure the AI cannot execute unauthorized calculations in the background, the hardware employs a method called governance by scarcity. The system utilizes an orange code CPU cap. A field-programmable gate array hard locks the compute resources available to the AI at exactly 1.1 times its baseline requirement. This restriction is not a software setting. It is mathematically verified using external tower draw monitors to measure the exact voltage and current, proving the resource lock in physical reality. If the AI attempts to spin up a complex, autonomous pathfinding inference, it hits this strict electrical power ceiling and is physically starved of the resources required to complete the calculation. Motion is never an automatic output. The system is physically denied the electrical power needed to actuate a rogue command. To transition the machine from this baseline stillness into a state of authorized motion, the system requires explicit human sovereignty. All high-risk kinetic interventions are gated behind the Tripartite 1X key latch. This latch is a literal hardware AND gate. It demands 3 simultaneous, verifiable physical inputs before it will allow current to flow to the actuators. The first factor is biological identity. The clinician must provide an optical iris scan, generating a hardware token that strictly expires in under 5 seconds. The second factor is cryptographic intent, verified via a dedicated hardware USB token. The third factor is physical presence. The clinician must maintain continuous depression of a foot pedal, wired with a dry contact switch, ensuring they are at the bedside. Because these inputs must close a physical electrical circuit, no amount of software compromise or algorithmic hallucination can bypass the human authority required to start the machine. If an anomaly occurs mid-transfer, such as a torque limit breach or a 5% positional variance between dual absolute encoders, the system must react instantly. At the exact moment of variance, the U7 sovereign brake triggers. It completely bypasses the control software and the operating system. The governance FPGA immediately fires opto-isolated solid-state relays, severing the primary high-voltage direct current power rails feeding the actuators. This electrical severance is canonical. The logic level drops and actuator power is physically cut in under 1.05 milliseconds. Once the power rails drop, the second phase of the shutdown engages the mechanical components. The loss of power automatically releases heavy-duty compressed die springs, forcing friction clamping discs to instantly bite down onto the drive shaft. This completes a total mechanical halt in under 50 milliseconds, locking the apparatus and its zero-creep lead screws to prevent any downward drift of the payload. The U7 sovereign brake ensures the machine halts physically faster than any software hallucination can propagate into movement. Following any emergency stop in a clinical environment, regulators demand an absolute, mathematically verifiable account of what caused the fault. Standard digital logs are insufficient. They exist as mutable files that can be scrubbed, edited by an administrator, or overwritten during a network breach. To provide forensic finality, the architecture utilizes the WD117 Write Once, Read Many ledger. Fault data flows through a physically unidirectional memory gate. With zero return copper traces, it can only record, it cannot issue commands. The ledger uses a dedicated laser circuit to physically scorch a cryptographic hash into one-time programmable silicon fuses. Because the silicon itself is physically burned and broken, retroactive editing becomes a thermodynamic impossibility, providing investigators with an unalterable, perfectly defensible audit trail. These mechanisms stack to form the complete security envelope of the architecture, integrating the D, N, and P layers into a single isolated hardware vault. The P layer enforces privacy by physics. It uses LiDAR to voxelize the patient's immediate environment directly at the silicon level, guaranteeing zero biometric capture without relying on software redaction. The N layer governs deterministic deliberation. It runs on a 1 kHz master clock that forces a mandatory physical delay, holding the machine in absolute stillness to guarantee time for human review. And the D layer provides cyber-physical defense, utilizing the U7 sovereign brake and the WD117 ledger as the ultimate physical fail-safes against agentic drift. Completely stripped of self-directed pathfinding and autonomous agency, the robotic platform acts purely as a highly governed, force-multiplying physical tool. This unyielding physical structure provides the exact mathematical certainty required by global health authorities. By hardwiring the safety boundaries, the architecture satisfies the strict regulatory mandates for high-risk HSA Class C and D medical devices, as well as Safety Integrity Level 3 standards. The core philosophy is absolute. The layout is the law. Clinical safety is no longer a probabilistic assumption. It is measured in physical reality. By replacing permeable software trust with immutable silicon physics, the Nightingale One Protocol bridges the practical deployment gap, finally bringing high-acuity automation safely to the clinical bedside. Probabilistic AI models are prone to hallucinations. In a chat interface, this results in a wrong answer. But when connected to high-torque clinical robotics, a hallucination translates directly into unregulated kinetic force. Software guardrails are structurally insufficient for physical safety. Code is permeable, and as autonomous systems experience agentic drift, these digital boundaries can be bypassed or rewritten by the model itself. The NAIGE architecture addresses this by removing safety governance from the software domain. Under this framework, clinical AI safety is an observable fact, measured in physical reality rather than a software claim. This shift moves governance from the permeable software cloud on the left to the immutable hardware vault on the right. Safety is enforced through unalterable silicon. Unauthorized actuation attempts are halted by physical air gaps and hardware gates that remain constant regardless of software state. Software alignment can be bypassed through code-level failure. Hardware isolation enforces safety through physical constraints, providing a level of reliability that permeable code cannot replicate.
Traditional autonomous systems grant AI both the intelligence to propose an action and the authority to execute it, creating a dangerous single point of failure. The inversion triangle doctrine strips the AI of execution rights. In this hierarchy, intelligence proposes, hardware governs, and the human decider maintains ultimate control. The AI proposes trajectories, the hardware monitors physical constraints, and the human operator determines if movement proceeds. This inversion establishes a baseline state for the system defined by the P-Life 1.00 doctrine. P-Life 1.00 mandates that the machine defaults to mechanical stillness. This is maintained by physically de-energizing joint brakes and releasing heavy-duty springs that clamp the mechanism. Motion is not an automated state. It is a hardware condition that must be explicitly unlocked through verified silicon gates. By making stillness the baseline, the architecture ensures that a dormant or compromised system remains inert, neutralizing the risk of unprompted rogue movement. If the machine is physically locked in stillness, the clinician requires a secure method to initiate movement during a procedure. Authorization requires the tripartite 0.1x key. This is a physical hardware circuit, not a software API call. The tripartite key is a hardwired AND gate. It demands 3 simultaneous physical inputs before power can reach the actuators. The first factor is biological identity, verified via an iris scan. This generates a secure token that expires in under 5 seconds to ensure the operator remains present. The second factor is cryptographic intent, which requires a physical HSM USB token inserted directly into the hardware enclosure. The third factor is physical presence, enforced by the continuous depression of a dry contact foot pedal wired to a hardware interrupt pin. Because this is a hardware AND gate, the circuit breaks if any single factor drops out. If the operator steps off the pedal, the gate snaps shut instantly. A hallucinating AI agent cannot press a foot pedal or forge a biological iris scan. This places sovereignty over motion strictly in the hands of the caregiver. Even with human authorization, a movement can become hazardous if the machine detects a torque spike or a boundary violation. Software-based emergency stops are often too slow and are vulnerable to the same code failures that caused the original error. The U7 sovereign brake provides immediate physical power severance through a sequential shutdown chain. The FPGA safety kernel monitors for hardware-level anomalies, such as an encoder mismatch greater than 5%. It asserts a fault trigger in under 0.1 milliseconds. At 1.05 milliseconds, an opto-isolated solid-state relay opens, dropping the motor rail voltage to 0. Power is physically severed. Within 5 milliseconds, the electromagnetic brake coils de-energize. This releases heavy-duty compressed die springs. These springs force pawls to clamp the joint, arresting all movement in under 50 milliseconds. This mechanical stopping power arrests movement even under a 200 kilogram load, completing the transition to P-Life 1.00. This shutdown state is physically irreversible until a certified clinician performs a manual on-site mechanical reset. The system fails safe according to the laws of physics, neutralizing kinetic threats faster than a human could perceive them. After a fault event, investigators must reliably identify the cause of the failure. Standard software logs are inadequate for clinical investigation because they can be altered or erased by a compromised system. To ensure accountability, the architecture utilizes the WD117 Write Once, Read Many ledger. This diagram shows the one-way flow of forensic data. The ledger receives information through a memory gate, while the outbound path is blocked by the hardware design. Data is cryptographically sealed using SHA-3512 hashes, anchored by the system's root of trust. System actions are scorched into one-time programmable silicon fuses, creating a permanent record that cannot be digitally overwritten. The lack of outbound command traces ensures the ledger can only record data. It is physically incapable of sending instructions back to the safety core. Replacing editable logs with scorched silicon renders retroactive tampering impossible, providing a legally defensible forensic record. This philosophy of determinism begins in the manufacturing pipeline, where the hardware is originally fabricated. Editable CAD models can lead to dangerous interpretation errors at the foundry level. Even microscopic deviations in component spacing can compromise safety logic. The NAIGE architecture utilizes the STEP ISO 10303 boundary representation protocol to eliminate this variance. Programmatic safety constraints, such as a mandatory 3.0 mm air gap, are compiled into rigid, unalterable physical dimensions. This creates a physical contract. If the foundry alters a single geometric tolerance, the safety logic physically breaks and the manifest is voided. The layout is the law. The hardware is designed to enforce safety constraints before the machine is ever assembled. The architecture provides a complete journey from the baseline stillness of P-Life 1.00 through the tripartite authorization gate and into the U7 break and the WD117 ledger. These isolated components form a multi-layered barrier that physically confines the AI. Clinical AI safety cannot rely on probabilistic software claims. It must be an immutable property of physical hardware. The NAIGE framework demonstrates an architectural method for deploying forceful robotics while maintaining a human-centric control loop. It ensures we can utilize advanced technology without surrendering human sovereignty over motion.